What's up, everyone, and welcome to this session where we build a linear regression model and a deep neural network to predict the current price of a second-hand car based on the number of years that car has been used, its number of kilometers traveled, its rating, condition, economy, the present state of the economy, top speed, horsepower, and torque. And so we're gonna build models which, when given these inputs, permit us predict this current price, as we could see in these results right here, where we have in blue the model's predictions and in orange the actual price. So don't forget to subscribe to this channel and hit that notification button so you don't miss amazing content like this. Before moving on, it's important to note that we are gonna follow this machine learning development life cycle, where we start with defining the task. We'll look at the data source. We're going to prepare the data, build machine learning models which permit us learn from this data, choose the right error functions for this learning process, and then get into the training and optimization. From here, we're going to measure the performance of the model on this data. We're going to validate and test our model, and then finally we are going to take up some corrective measures to improve the performance of this model. Our task here is to predict the price of the used car using some input features. In this case, we've selected just one feature, that is, say, the horsepower. So supposing we have this, and then we have the price in $1,000, and then we want to make use of this input data right here, that is this horsepower and the corresponding prices, to train a model such that when given the horsepower, we'll be able to predict the corresponding price of that used car. Or when given this 150, we'll be able to predict the price of that used car based on a model which has been trained on this data right here. Plotting out this data, we could have this on the x-axis and then the price on the y-axis. As you could see on this plot, based on a given horsepower, we are able to predict that the price of the second-hand car. Now, if we draw points like this, if we draw lines like this from these points, you see that we have a continuous range of real valued outputs right here. And since our outputs here can take up continuous values, we term our task as a regression task. Now let's modify this problem so that you better understand the regression problem. Yeah, we have this horsepower, and then if we modify this such that we are gonna instead predict whether the car is gonna have the car is gonna be noted as expensive or not. So instead of predicting the price, we may want to predict whether that car is expensive or not. So let's say for all cars below, say 8, let's say 8.5, they are cheap, and then so we'll call that cheap C, and then greater than 8.5 we have the expensive cars. So here we have greater than equals to, here we have cheap, here is expensive. And so from here we may have a different kind of task, that is one in which we want to say, if based on some input or some inputs, because you may have many inputs right here, based on the inputs, the car falls under one of these categories right here. So you could see that this kind of problem is one in which our outputs are discrete. See, you have just two options. And then with this problem where we're trying to predict the price, we don't just have some 2 or 3 or 4 options which we want to pick from. We have an infinite number of options, since the prices can go from, let's say, $1,000. We suppose that we fix the minimum to $1,000 and then the maximum to $100,000. So we could fix this to 100K, from 1,000 to 100,000, but the values fall under this range, which is actually an infinite number of possibilities, unlike here where we have a finite number of possibilities. We now move on to the data, and before diving into that, let's look at the big picture. So here we are having a model which is going to fed in this inputs and the outputs, such that later on we could have this inputs fed and then we obtain the outputs. Notice the difference, the change in direction of the arrows. So initially we have this inputs, so we could have this inputs right here. Let's take this off. We could have this inputs, that is this x and then this y. So here we go, we have this inputs, and then after the model trains, we will now pass in just this, and then we get this one automatically. So let's get straight away into how we're gonna prepare this data such that it could be passed into this model right here. Here we have the second-hand cars data set made available on the Kaggle platform by Mayank Patel. Here we have a description of our data set. So we have these different features which we'll be using to predict the price of the second-hand car. So that said, you could see here, you could get more details. So basically here's our data set, as you could see. And then by clicking on this, so you could sort, and then you could get to this compact view, column view. Here you see that we have the ID, which is we're not going to use this because this is actually not part of our data set, but just an ID. Then we have this on-road old feature right here, though it's not actually well explained because we don't clearly see exactly what it signifies. Nonetheless, we have, let's take this off, we have this mean and the standard deviation. So as we had seen in the previous video, we could have this, and most of our values are around the mean. That is, most values we get in this data set for the on-road old feature lie between the mean, this is mu, the mean, and sigma, the standard deviation, lie between the mean minus the standard deviation and the mean plus the standard deviation. So in this range we have most of the values. So this simply means most of our values lie between 602k, as we could see there, plus, or rather 602k minus 558.4k. So that should be about 543.6. So if you subtract this 58.4, we have 543.6. So this means our values fall in this range. Now most of our values fall in the range 543.6 and 602 plus 58.4. So that is 660.4. So most of our values fall in this range right here. So that's what we mean by having this mean and the standard deviation. So we're gonna have this same right here. Now we have other features. Let's take this off. We have other features, as you could see. We have on-road old and on-road now, which wasn't very well explained. We wouldn't use this. And then we have the number of years. That's obviously the number of years of usage of the car. You see we have missing, number of missing values. We have known, number of mismatches known, and valid 1,000. So this is kind of like cleaned data. We have the mean, that is 4.56 years, and the standard deviation 1.72 years. So most of our cars in this data set have been used for, most of them will fall under the range for the 4.56 minus 1.72 and 4.56 plus 1.72 years. So number of kilometers covered, there we go. We have the rating, that's the car rating at the moment you want to buy it, the condition at the moment you want to buy it. You see the mean right here, the current state of the economy, the top speed of the car, the car's horsepower, and that's it. So here are the different features we have and which we will use in predicting a car's current price. So that said, we could download this for free. So we have this downloaded. we now get into our Colab notebook where we're going to do the preparation of this data. So here we have these three inputs. We have TensorFlow for our models, we have pandas for reading and processing data, we have Sequential. This is going to be for visualization. So that's it. Now you don't need to have any prior knowledge on this tool, as we're going to explain every single step of our data preparation and visualization processes. We've now uploaded our data set right here, this train.csv file, which we downloaded from the Kaggle platform. You could see it right here. So double clicking on this gives us this file we have here. Now we click on 100. Yeah, we have 10 per page. Okay, let's say we want to get 100 per page. So that's it. We have this different data points right here. Now that said, as we could see, we have the ID, on road old, on road now, the years, number of kilometers, rating, conditions, economy, top speed, HP, torque, and then the current price. So that's it. That's for each and every data point. And now let's do this. So let's break this up. So we could do this, we could break this up. So if we break this up like this, you see we have this first section, our inputs, and we have this other sections right here, all this other section. Actually, we have this section, our outputs. So here is now our X, and here we have the Y. Here, if we suppose that we have totally n data points, that is, if we have if we count all these data points and we have n of them, then we could have this shape, or we could represent these inputs in a tensor of shape n by, yeah, we're not taking this, we're not going to take this column, we're not going to take less, we're not going to take this column, we're not going to use this column because we don't understand it very well. We're not going to use this, we're going to use this. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So we have n by 8. That's it. That's our input X. That's the shape of our input X. And here we have n by 1. So this is the shape of our output tensor. If you're able to put this data which you've been given the CSV file in the form of a tensor with the shapes, then you could pass this now into a model like this. Let's call this M a model. Pass this in and then train this model such that when you come now with new data, the model is able to predict the current price. Now, to read CSV files, we are going to make use of this pandas library right here. See, we've defined, or we've imported this as PD. So that's why we're having this here. So this is practically pandas. And then we have read CSV. So this method is used in reading CSV files like the train.csv file we have here. And then we specify the separator. Let's open up this file with Excel. There we go. Yes, what we get is very similar to what we've seen already. Let's close this up. And now let's open this up with Notepad. So, okay, that's it. So you'll notice now that this is our same data, but the way it's put out is quite different. As you could see, all our column heads are separated by this commas. So we separate each column by a comma. You can see that clearly from this. And then when you go to the next row, we also have the separation by commas. Let's do this. Let's put this link. So we see this one, see it linked right here. We have this number right here linked to this. We have this next number linked to this, and so on and so forth. So that's it. And that's why we are having comma separated values format. So this is the meaning of the CSV format. Comma separated values. So we see each and every value is separated by a comma. That's each and every value which makes up this row is separated by a comma. And that's how CSVs are formed. And you should now understand why in this code when we read the CSV, we specify that our values are separated by commas. Now, in the case where you have data and then you have something like this, so you may have this semicolons everywhere. So let's say we have the semicolons. We're gonna save it as a different file. So we could have the semicolons. There we go. We now have all this separated as colons, or separated with the semicolons. We save this, and we've now uploaded it right here. So that's what we have. See, we have this right here. Now let's go ahead and read this. So we've created this data, and we could say data.head. You see data.head. We run that, and you see we get the first 5 rows of our data. And straight away you could already do stuff like this, data.shape. You see we already get the shape of our data. We have 1000 by 12. Now let's get it a semi. So let's just copy this. So we'll copy that and paste it out here, and then let's run it with, supposing our values are separated by commas. So let's run that, and this is what we get. You see we have this head, which is not actually well formatted, because by default this formatting is meant for comma separated values. Now what if we modify this? We run that again, and you notice that there is a difference actually now. So let's do this side by side. Let's run that. Let's take this back to comma. So we have that, and you notice that there's a difference now. Here is well formatted, whereas here is not very well formatted. So that said, if you want to work with these kinds of data, you could always make use of the pandas library. Let's print out data.shape here. We run that, and then here we print out, let's say data.shape. So let's have that. See, here we have 1 by 1, which is not exactly what we expect to get. We've now been able to read our data and then put this data in some sort of data structure. Let's now visualize how each and every feature right here is related with each other. And to do this, we're going to use the Seaborn library right here. So Seaborn has been imported as SNS. So we have sns.pairplot, which we have here, sns.pairplot. We pass in our data, and then we have all these features with the output. You could check out the Seaborn.pairplot documentation on the Seaborn website. So right here you have the different parameters. You have the data, you have the hue, which has to do with coloring, and then we have this data kind, which we used. And the data kind was a kind of plot for the diagonal subplots, which we're going to see shortly. So here, as we see, we've selected a KDE. We run this. The KDE actually stands for kernel density estimate. After running this is what we get. We see this KDE plots in the diagonal. Now let's look at each and every one of this. So let's take off this IDs, because we're not going to be using this. ID on-road old, on-road now. That's because we don't understand exactly what they signify. So we will run this again. Here's what we have now. Let's scroll up a bit, and now we'll see we have the number of years, and this plot here shows us how the number of years is related to the number of years. You see how this is related to the number of years. In the diagonal we have how each feature is related to itself. So let's reduce this. Okay, so here you could see how this, okay, so you see how here we have this years related to years, here we have kilometers related to kilometers, radians to radians, and so on and so forth. So that was the diagonal. That was a KDE plot. Now here we have how the years is related to the kilometers. So we see how, okay, let's take it from this. So we have here this kilometers, and then how the years related to the kilometers. Here we have years related to the radians, and you repeat the same process to get all those relationships between these different features. But one very interesting point to note here is we could already see the relationship between these different features and the current price. So let's take, for example, here we have current price. So this is a plot showing how the number of years is related to the current price. And this is based on the data we have. We see clearly from here that for each number of years spent, the current price could go from very low to very high. Now, if we move to the kilometers, you see a certain pattern. You notice that as we increase in the number of kilometers covered by the car, the overall current price of the car drops. So this is one very interesting feature to note. We see a similar pattern to this years with the rating, the condition, the economy, the top speed, HP, and torque. So here is how each feature is related to the current price. At this point, we convert our data into a tensor. So we have tensor data equals tf.constant, and we take in this data. So we do this and we run that, and there we go. We have our tensor data. So that's it. Let's print out this without a shape. So we have that. There we go. We see we have our tensor of type float 64. Obviously, you could do some casting. So we could say tensor data equals tf.cast of tensor data, and then we specify we want to have an int, say, or rather we want to have a float, say 16. So let's run that again. A problem which arises now is we have some values which are converted into infinity. The reason why we have this is because some of these values are too large to be stored as float 16 data types. So we're going to put this 32. You see, we run that and everything is intact. Another important step to take is to randomly shuffle our data. So to avoid any bias based on the way in which the data was gathered, we do this random shuffling such that this order right here is no longer respected. So let's do that. What we need to do, we have our tensor data is now equals tf.random.shuffle. So we have that and we pass in tensor data. That's it. Let's print out tensor data. Let's say we print out the first 5 elements. So let's print that out. Here's what we get. But then let's copy this so you could see the difference before and after the shuffling. So let's say we have this. Let's take this off. Let's have that. And then we have our tensor data. Let's run this again. We print out our tensor data. You see, we have this. And then we print out this shuffled tensor data. You see that here this ID order was respected, 1, 2, 3, and so on and so forth. Whereas here we have 551, 567, 229, 557, 402. So we've actually shuffled our data, and then let's take this off now. So we've shuffled our data, and then we're ready to break this data up such that we have both the inputs, that's X, and the outputs Y, or the output Y. Before continuing, let's add this little text here. So we have this text, we add a text, and we say we're doing data preparation. So that's it. Put that in bold and we're fine. So we have that data preparation. Now right here, as we're saying, we need to get this X and the Y. Let's start by getting the X. So here we have X tensor data. That's it. And then we pick out all the rows. So obviously we're interested in getting all the rows. We're interested in getting all our 1,000 or 1,000 rows. But then we're not interested in some columns. We're not interested in this column, this column, this column, and this column. So we're interested in just this, or rather this. So that said, we have here 0, 1, 2, 3. So we're going to take from 3 right up to this position right here. So that's it. So we do that. We just have here, we pick out everything, and then in this next we have 3 right up to -1. So let's print out a shape. Before printing out the shape, let's look at this and get that shape before printing it out. So normally we should have 1000 by 12, but since we're picking out just the inputs, now we have 1000 by 1, 2, 3, 4, 5, 6, 7, 8. So we have now 1000 by 8. So running this should give us just that. We run that, and there we go. We have 1000 by 8. If you print this out, let's print out the first 5. We have that. There we go. We have just this now. Notice how here this first 3 values have been taken off, and we're left with this right up to this value. So that's it. And then the current price too has been taken off. We repeat the same process to get the output. So here we have Y. That's it. Okay, but now we get in all the rows. That's true, but we get in just that last column. So that's it. Yeah, we'll print out Y, and that's fine. So that's what we get for Y. Notice that here we have the shape, which is actually just 1D. So what we could do is, after getting this, we could expand themes. So we have tf.expand themes to add that extra dimension. So we have tf.expand themes, and then we put that, we specify the axis. Here we have -1. So we rerun that again, and what do we get? This is what we get. We have 5 by 1, just like here we have shape 5 by 8. Now we have 5 by 1, unlike previously where we had just this 1D shape. Let's take this 5 here. So previously we had just this 1D shape. Now we've added this extra dimension so that it matches that of the inputs we have here. From this point, another very common transformation which we could do on our data to enable our model train faster is by normalizing this data. In fact, we actually normalizing the inputs. That is, we take for every input, we subtract the mean, and we divide by the standard deviation. In this example here, the mean of this 8 values is around 138. So that means if we want to normalize this data, we're going to have 109 minus 138 divided by the standard deviation. Let's say the standard deviation is 150, for example. So this means this point is going to be converted into negative 0.193. If we now take a value like 206, we're going to have 206 minus 138 divided by 150, which will now give us around 0.45. So if you notice, our input features have been rescaled before passing into the model. And to carry out this feature scaling, TensorFlow has this normalization layer right here, which is part of the tf.keras.layers. Now, we haven't spoken much about tf.keras because we have not gotten into the modeling. But for now, just note that in this tf.keras.layers, we have this normalization class, which can be defined by specifying an axis, the mean, and the variance. That's it. We have from TensorFlow.keras.layers, we are going to import normalization. So that's it. Let's run that, and then we get to use this normalization layer. Before looking at our data, let's see how we could use this normalization layer. We define a normalizer, and then we have normalization. We pass in nothing inside there. By default, the axis is -1. We'll look at that shortly. And then here, we're gonna have the x to be normalized. So we have x to be normalized, which is this TensorFlow tensor right here. Let's say we want to have 3, 4, 5, 6, 7. There we go. And then we do normalizer and we pass in x to be normalized. So that's it. We have passed this and we see we have exactly the same output. That's because here we haven't specified the mean and the variance. So we just have this, the input passed as the output. Now let's go ahead and specify the mean. So if we say we want to have a mean of, if we look at this, let's say 5, and then the variance of say 4, we run that, and there we go. What do we notice? We notice that these inputs are being rescaled into this new inputs. Now let's add another row right here. So we want to have 4, say 5, 6, 7. Let's keep it simple. So we have this, okay, let's say 8. So we have this next row. That's it. And what do? We run this. Let's correct that. There we go. We run that and we see we have this normalized properly. Though it's worth noting that since by default the axis is equals -1, so by default we have this axis equal -1, it means this normalization here is done with respect to the columns. So if you could recall from our previous section, we have our shape 2 by 5, and picking the axis -1 means we're picking this axis here, and this actually corresponds to the columns. That's 1, 2, 3, 4, 5. So we have our 5 columns, and then for each column we are doing the normalization. So practically what we're doing here, we're doing 3 minus 5 divided by the variance which we've picked, we normalize that. 4 minus 5 divided by the variance 4, we have the value, and so on and so forth. We've made a slight error in this definition. It's actually x minus the mean divided by the standard deviation. So it's not the variance, it's not divided by the variance but the standard deviation. Now we also know that the standard deviation squared is equals the variance. So basically when we have this variance, to obtain the standard deviation we simply find the square root of our variance. So in this case our variance is 4, so standard deviation is 2. If we replace here by 2, our mean is 5. That's it. And now let's pick x. Let's take x, for example, to be this 3 right here. So if we have 3, you see when you run 3 you should have -1, and if you pick 4 you should have -0.5. so that's it. So that's how we get this. Now let's take another example, but in this example we don't specify the mean and the variance. Now you should note that it's not in every situation where you could get the mean and the variance up front. So there are some cases, or in fact in most cases, you just have the data. So you wouldn't always go and calculate this mean and variance up front. So what TensorFlow allows us to do is to obtain this mean and variance automatically. So the TensorFlow permits us to adapt to the data we're given. So if we're given this data, for example, what we're gonna do is get the mean and variance for this column. That's this column right here, made of 34, and then get the mean and variance for this column, for this column, this column, this column, and be able to normalize our data. So just like here where we suppose the mean and variance for each and every column was 5, 4, here we're gonna get the mean and variance for each and every column gotten automatically. So let's look at that. We don't need to put a mean and variance now, so we just let that go. We could take this off too. since by default the x is already -1. So we have that, and then what we do is we do normalizer.adapt. So we're gonna adapt to this our data. We adapt to the normalized data, and then we pass the normalizer, we pass x normalize in this to obtain this now. So this is what we obtain when we adapt automatically to our data. Now let's understand what goes on. We have 3 and 4. Here the mean is 3.5, so that's clear. So we have x minus 3.5 and divided by the standard deviation. If we have two values, 3 and 4, it's clear that a mean is going to be 3.5. That's going to be in the middle. And then if we have a mean of 3.5, so we have something like this, our standard deviation should be 3.5 minus 0.5 gives us 3. So here we have our mean minus the standard deviation to give our least possible value. So here we have a standard deviation of 0.5, such that 3.5 minus the standard deviation gives us 3, and still 0.5, such that 3.5 plus 0.5 gives us 4. So that's it. So coming back here, if we take this 0.5 and we put in the value 3, we run that, you see we should let's correct this, you see we have -1. So that's how we have -1 here. And when we put 4, you see we have 1. Now if we move to this next, 4 and 5, and we maintain the same mean and standard deviation, you see we wouldn't get those answers right. So let's take this with 5. You see here we have 3, which is not what we get here. See, when we have 5 is transformed to 1, and this is made possible because we get the mean and the variance for each and every column. So that said, when it's 4 and 5, we have a mean of 4.5, standard deviation 0.5. So if we change this now, 4.5, 0.5, we put this to 4, you see we have -1 again, and then 5, we have 1. So if we modify this now, let's take this to, let's say 10. Let's run that. What do you see? We have -1, 1. Why do we have this? Is because the mean of this is 7. So yeah, we're gonna have a mean of 7. We're gonna have a standard deviation of 3. When we have 10, we run that. We see we have 1 still, and then with 4, we have -1 still. We could go ahead and add now one extra row. So let's say 32, 1, that, and this. Let's run this again, and we see that we have our normalized data right here, which has been done automatically, unlike where we needed to specify the mean for each and every column. Here our normalizer adapts to our input data. So how is all this related to what we've been doing? Here all we need to do is we've been given x, so we have x. Recall, we're not doing normalization on the y, obviously we're doing this on the inputs. So we are having our inputs x, which we've gotten already. So we could print out the shape. Let's take this off, print out the shape of x shape. You see we have, correct that, we have 1000 by 8. So we're gonna normalize for each of these 8 columns. And instead of struggling to get the mean and variance for each of these columns, TensorFlow permits us to adapt to this, our data set. So that said, we have that given to us. We could just recopy this. Oops, we have that. Paste that out. We have our normalization, normalized. This is actually x, so we don't need to specify this anymore. So here we just adapt to x, and that's it. Let's print out this x so we see the kind of outputs we get. Let's say we want to get the first 5 elements again. So that's it. So what do we see? We have that, and then let's print out x, first 5 elements, or first 5 rows. There we go. So here we see we have this 5, which is converted to 0.25. We have this 4 to -0.232, and so on and so forth. So this has been done automatically, and we are now ready to train our model using this normalized data. We've gotten to the point where we're going to train the machine learning model. In our case, our model is simply this straight line right here of the form of equation y equals mx plus c. As you could see here, we have this inputs x, so there we go, inputs x, outputs y, and we have our weights m and c, which happen to be these constants. That said, we have an x which gets in here, it gets multiplied by m, so we have a multiplication by m, and then we obtain mx, so now we have mx, and then it gets added to c, so here we have multiplication and here we have addition, and this gives us y, which actually equals mx plus c. So let's say it gives us mx plus c. Let's take this off. We have mx, and then we put all this into a box, which is what we call our model. Now notice here, let's have this. We have our model, we have x get into our model, and we have our output right here. And then what we're trying to do is to get the most appropriate values for m and c, such that we have an output which best represents our data set. So that said, our model could be represented by this line. So we could have a model like this, we could have this, we could have this. You see, we have so many different possibilities. And so when we're talking about a model, essentially what we're having is a function which tries to be representative of our data set. Now this means, if let's take this off, this means if we have a model like this, clearly this isn't a very good model, or this is a very poor model, since it doesn't actually represent, it doesn't embody the data set we have in here. And so a model looking like this will be a better one. For now, we'll just stick to the model creation, but we should note that this model has to be chosen such that it represents best our data set. So we're going to look at this in the error management and training and optimization sections. And before we get there, that is before we see how to get the optimal values for m and c, we are going to create this model using TensorFlow. The good news is TensorFlow makes it very easy for us to create deep learning models. So here we can define our model, TensorFlow.keras.sequential. So we have that, and then we pass in our normalizer, and we have a dense layer. So here we have a dense layer which takes in an output of 1. Now this dense layer is actually a Keras layer. So let's get in here. So from TensorFlow.keras layers, we imported normalization previously. Now we import the dense layer. So we have dense, we run that again, and right here we have our model summary. There we go. We could visualize this model. We've just created our first ever model with TensorFlow. So let's break all this down. Now we have this sequential API which we use here in creating this model. This is just one out of 3 different ways in which models are generally created with TensorFlow. We have the sequential API, we have the functional API, and then we have the subclassing method. So that's it. For now, we'll work with the sequential API. We could look at the documentation for the sequential API in the TensorFlow.keras model. So right here we have this sequential. We click on that, and there we go. So basically what this takes in is just layers. And here we have some examples on how this is used. So that said, you could see we define a model and then we add layers to this model. So basically we're just stacking up layers to this model. Now this means instead of having this syntax right here, we could instead have this. So we could take this off. We take this off. We have that, and then we have model.add tf.keras, or let's just say normalizer. So we add the normalizer, and then model.add the dense layer. So we have our dense layer, output 1, and that's it. Let's run this, and we get exactly the same output we had right here. Now let's take this off and get back to our sequential API. So as the word goes, is the way we build models when layers all form a sequence. That is, if you're building deep learning models where the way they are constructed is such that we have the input, we have the model, we have the output, and then all the layers which make up this model are simply just stacked up one layer after another. So we could have this layers which all form the model. We'll look at more complex layers later, but for now, let's suppose we have this kind of model made of different layers, layer 1, layer 2, up to layer n, where we just simply stack up these layers in this way. Then working with a sequential API is a good option. Now let's take this off. Let's take this and then make use of the exact model we're actually currently dealing with. Right here we have this model and we have this other model. So we have or rather we have this layer and we have this other layer. Right here we have the normalization layer, which we've seen already. We understand that our inputs need to be normalized before being passed into our dense layer right here. So here we actually have this dense layer, but then this should be the first time, or maybe it's the first time you get in of this dense layer. So we try to explain what goes on in this dense layer, but you should note that this model is simply made of the normalization layer and the dense layer. So we're done with the normalization layer. Let's look at how the dense layer works. With a dense layer, as you could see here, let's suppose we have an input. So we have the horsepower input getting in here. We have our input. Then in this dense layer, we take this input, the horsepower, which we call x, multiply it by m, and then add a value c. This m happens to be the weight, and then the c is what we call the bias. So that said, we have this, and then here we have mx plus c. So here's our output, which is actually equals y predicted. So let's call this y predicted, and that's it. So what do we do now when we have many variables? Once we have many variables, we still have our same dense layer, but there's a difference. So here we have this variable. Let's suppose we have 8 variables. So we have 1, 2, 3. There we go. We have this 8 variables. Now all these get into our dense layer. So we pass this into our dense layer. Then what goes on in this dense layer is that for each of these inputs, we have this M1, M2, M3, M4, M5 up to M8. And we have this M1 times X. So we have M1X, similar to what we had here. Here we just had one M since we had one input. But now we have M1 times X. That's the input here. Let's say X1 plus up to M8X8. Then we add that bias. So we add this bias C right here, and then we have plus C. So here's our dense layer right here. This is exactly what goes on in our dense layer. And then we have obviously our output y predicted. So that's it. We now understand exactly how this dense layer works. Now you'll notice that we have 1, 2, 3, 4, 5, 6, 7, 8 weights plus this bias, making us 9 different parameters. And that's why right here you actually had this 9 params given to you. You have this non-trainable param 17. This comes from the normalization layer. Now it's non-trainable simply because we've already fitted this normalization layer to our data, or we've adapted this normalization layer to our data, so we don't need to modify the parameters mu and variance anymore. We don't need to modify the mean and the variance anymore actually. So that's it. We understand exactly what's going on and why we have 9 trainable parameters here. So from here we should note that the way we construct the dense layer is quite simple. All you need to do is to say how many outputs do I need to have. Now in our case we just want to output the current price, and since we want to output this current price, which is just one value, our number of outputs here equal 1. So that's why we pick this number of outputs to be equal 1. Now if we needed to predict say 2 current prices, or maybe we needed to predict the current price now and the current price in the year say 2030, then we would have output 2. So that's it. We just have one output. That's why we do that. From here we have this model.summary, which we can call very easily and see this kind of interesting summaries of our model. So that's it. We now look at how to plot this model out. That's quite easy. We have tensorflow.keras.utils plot model, and now we pass in our model. We specify to file. We want to plot this model out and then generate a file. So we just say model.png show shapes. There we go. True. So we want to show shapes. We run that. We see clearly here we have an input layer, we have our normalization and our dense layer. Notice how the inputs and the output has been specified. So this known here is actually the batch dimension, and since we could treat data of any batch size, we just have this as known. Now what's our batch size? You see our full data set we had right here. Generally we are not going to load all this data set at once into our model, as we may be limited by memory requirements. So that said, what we pass into our model is actually passed in batches. So we could work in batches of 2, so we could just pass out just 2 values or 2 of these data points into our model. We could pass just this 2 and so on and so forth. If our batch size is say 8, we just pass all this into our model at once and then move to the next batch and so on and so forth. But now note that generally you will not want to have a very large batch size, as this will lead to a problem known as overfitting, which we'll treat subsequently in this course. But for now, just note that working with batch sizes of 32 and below is actually a good idea. So let's come back to our model which we had here. We now understand why we have this knowns here. This is actually our batch dimension. Now we could also, in addition to this normalizer, or before the normalizer, we define an input layer. So let's just declare this here. Let's just add this here. Let's import this. We have input layer. There we go. So we have our input layer, which we're gonna add from this Keras layers. If you notice here, we just had this known. So our inputs are not specified. The input shape is not specified. The output shape not specified. So what if we come and specify this? Here we have input layer. Sorry, we have this, and then we have the input shape, which we could specify. So here we have a shape of the batch by 8. So we have a batch dimension. So if it's 32, we have 32 by 8. So this is what's getting to our model at once, and not maybe the whole 1,000 samples we have. So instead of sending all this, we send just a batch of 32. Now when creating this input layer, since obviously up front we don't know the exact batch size, we'll take this off and just have that. So we just have this shape, we pass that, we have this error. Let's add a comma, and we also have to know that this is a list we're passing in. So we have this first element of the list, this next element on this other element. Either we do this or we use the model.add option, which we saw already. So we run this. Let's have this here, and there we go. So we see we have exactly the same kind of response as previously, and then let's run this again so we see this difference. Now we notice that we don't have known again here. Now we know exactly the shape of our inputs. So that said, we could now get straight away to the next section, which is that of error sanctioning. So at this point, we've we've built a model, as you could see, y equals mx plus c, and we'll now see how to know how well or how representative this model is of our data set. So to check this out, you'll notice that for each and every output we have, so supposing we have this point right here, we are going to compare the actual output with what the model gives us. So our model tells us that at this point, so we had this x, this is x axis, at this point right here, we should have, or what our model tells us is we should have this output at this. So this is our selling price according to the model. But then what we actually have is this. So what comes from our data set, or the actual selling price, is at this point. If we look at this other point right here, you'll see that our model does quite well, as our model, or the actual price, is this. And if we extrapolate, we see our model tells us our price is this. So the actual price and the model's price is quite similar. Now if you take another point like this, you see this performs poorly here. Our model tells us we should be around this selling price, and the actual selling price is around this. So this tells us that if we want to choose the best possible values for M and C, then we have to choose them such that we minimize these differences. So these differences we have here, this is what the model gives. So we have to try to minimize these differences. By minimizing the differences, we actually sanctioning this error. So we sanctioning the model every time it makes these kinds of errors. So with these kinds of large errors we have here, we're trying to sanction the model. And then when we kind of like work perfectly like this, our model receives less sanction, or in the case where it's actually perfect, our model receives no sanction. That said, this sanctioning is actually quite simple. Like what we'll do is, when you have an error, or simply let's say we have an output, so we have this error, but the way we calculated this error was we have an output, and then we have we have the actual output, and we have the model's predicted output. So we have the actual output here, let's call it YA, and then we have Y pred. So this is what our model produced right here. Now what we could do is we subtract this 2, and then we square this, and you see clearly that if the Y actual and the Y predicted are both the same, then in that case we'll have 0, because Y pred is the same, so YA minus Y pred is 0. And if we have 0, it means we are having to give that model a 0 sanction for that particular prediction, like in this case right here. Now if there's a very great difference between these two, then we are subtracting it and also squaring. So you see clearly that if you have maybe 2 and 4, so if our actual is 4 and what the model predicts is 2, then 2 minus 4 we would have, or rather 4 minus 2, anyway, actually, because we are going to square this, so we have 4 minus 2, we're going to give us 2, and if we just Y pred minus YA, we would have 2, but now we're squaring this, so we have 2 squared, so we now have 4. So we're squaring this error. So anytime we make an error, we amplify that error. Now if we want to get the overall error, we could use what we call the mean square error function. With the mean square error function, what we're basically doing is this, but we're repeating this for each and every point, and then we're finding the average of all those errors. And as usual, TensorFlow already has this built in, so all we need to do is just make use of this function which has already been built. Here we have our loss function. You notice that it's under the TensorFlow.keras, tf.keras. Let's scroll up here. We have tf.keras. We've seen the sequential. Now we're looking at the losses. So yeah, we have this losses. We could also check in this layers here, and you'll see that we have our dense layer. So we start to understand how this tf.keras section here is structured. So here we have our dense layer, which we've seen already, the number of output units. We're going to look at all this subsequently. For now, let's close this and get back to our mean square error. So here we have losses, mean squared error. That's it. There we go. We have here some examples. So we could look at this y true, that's the y actual, and the y predicted by our model. Now, doing a mean square error here, we have 0 minus 1, that is 1. 1 squared is 1. 1 minus 1, 0. We have 1 plus 0 plus 1. Obviously, 0 minus 1 is 1 is negative 1. Negative 1 squared is 1. So for now, we have 1 plus 1 because 0 minus 0 is 0. So when we will add up all this, we have 1 plus 1, that gives us 2. Now, how many different elements do we have? We have 4 elements. So 2 divided by 4, it gives us 0.5. So we've summed up all these square errors, and then we divide by the total number of elements we have, which in this case is 4. So that's exactly how we obtain the 0.5. Now we have that. We just simply come right here, and then we have from TensorFlow.keras.losses, we're gonna import our mean squared error. So that's it. Let's run that. That's fine, and we could make use of this mean square error now. The way we make use of this is actually when we compile in our model. So we have model.compile, and we define our loss. So our loss is a mean square error, which we've just defined. Mean square error, that's it. And what this does is, as we compile in our model, we take into consideration the fact that our error sanctioning function is going to be the mean squared error. Now, for regression tasks, apart from the mean square error, we also have the mean absolute error. And here, every time we do the subtraction of the y true, that's y actual, and the y predicted, instead of squaring this, what we do is we calculate the absolute value. So it's quite similar to what we've seen already with the mean square error. Just the only difference here is we have the absolute of the subtraction of the difference between the actual and the predicted value of y. To better understand when to use the mean square error or the mean average error, or rather the mean absolute error, let's take this example. You see, with this example, we have the horsepower and the current price. Most times, the horsepower is positively correlated to the current price. That is, if we increase the horsepower, generally or overall, we have an increase in the current price. And for a reduce the horsepower, we have an overall reduce in the current price. Now, we may have this point here, which is actually what we call an outlier. We see that we have a very high horsepower, but the price is very low. And in the case where we're using the mean square error, we'll be having y minus y, this ya, or let's say y actual, and then y pred. So we have y actual minus y pred, and then we're gonna square all this. You see that this is just one, or is kind of like a minority in our data set. And when modifying the weights of our model, we don't want these to weigh too much or to have so much priority in the way we choose the values for M and C. And so that said, using a loss function like this, which actually squares these errors, is not a good idea, because since this error here is going to be very large, so if we continue with this, we'll end around this. Let's suppose around this. So our model at this x, our model will predict something like this, will be around this, and then the actual will be around this. So we have this large error. Squaring this large error again gives us a very large value, and so this will have very much to say when we're picking out these values for M and C, as basically we're modifying these values based on this error. So based on the error, we're trying to modify the values such that we pick the values which minimize this error actually. And as we've said in the case of the mean square error, for these kinds of outliers, we making them too important when we should focus more on these other data points. Now with a mean average error, or with a mean absolute error, we have YA minus YP, and we compute the absolute value. Now here clearly we understand that our overall loss, or the loss we get with these kinds of outliers, is reduced compared to this, since here we just simply finding the absolute value, unlike here where we're squaring. And so in working with data sets where we have outliers like this, it's preferable to use the mean absolute error. Now there is a loss function known as a U-bar loss, which actually permits us make use of this mean square error and the mean absolute error in a more intelligent manner. That is, when we have an outlier, we are going to use the mean absolute error, but when we have a normal data point, we use the mean square error. By normal data point, we mean a point where the y true minus the y pred, which here is this x, isn't or is less than a given threshold. And by an outlier, we're talking about points where the y true minus y pred is greater than a certain threshold. So here we have the definition for the U-bar loss. We see how this x is actually y true minus y pred. So when computing the U-bar loss, if we have this condition, we use this variance of the mean square error, where we have 0.5 times this y true minus y pred square. And then when it's greater than d, so here we're dealing with outliers, that's this our threshold. When we're dealing with outliers, we have 0.5 times d squared, that's times this difference squared, plus this d times the absolute value of y true minus y pred minus d. So here's the formula, the U-bar loss formula. Again, we don't need to rewrite all this from scratch, since we have this with TensorFlow. So that said, all we need to define here is our delta, which is that threshold that defines whether a data point is an outlier or not. So here again, we have our losses, we have the U-bar loss, and then we have the mean average, or rather the mean absolute error. So that's it. This is actually U-bar simply. So we run that. There we go. So here we're gonna compile our model. Let's take this. We have the mean square, we have the mean absolute, and we could also have the U-bar. So if you run this, you see your model compiles. You could just simply specify U-bar, but we need to pass in our delta. So running this, we're using the default delta which was given to us. If we want to specify our own delta, we just specify it that way. So we could take 0.2 and stuff like that. So here we have the default data is actually 1, so that's it. Let's take this off. We're gonna be using the mean absolute error. Now note that with machine learning, we do a lot of experiments. So after we're gonna train our model, we're gonna measure its performance. And so if you measure the performance and you see that it isn't good enough, you could come and modify the error function you're using. So you could change the mean absolute error we're about to use to mean square error, or maybe to the Uber loss, and from there you try to see which loss functions permit you get the best possible performance for your model. From here we move on to training optimization. Recall our model was this linear function which we were trying to fit such that this here, this m and this x, or rather this m and this c right here, are picked such that these errors here are minimized. So just looking at this, we could have another line drawn here. We could have this line. We could have this other line. So we could have this other line, and so many, on infinite possibility of, or an infinite number of possible lines we could generate. And so in order to get this m and c, what we use, or the method commonly used today, is stochastic gradient descent. Now let's understand how this works. We'll just use this or write this out in this one formula. We have a weight which has to be updated. Recall that initially our weights are random, so we randomly initialize our weights. So this means here that if we randomly initialize m and c, and then let's suppose we have m to be 0, so we have m 0, and then let's say c is 1, then in that case we would have something like this. We would have a line like this, and it's clear that this line isn't very representative of this data we have here. And so what we could do now is to update this m and c such that the take up values which permit us adapt to this data set which we've been given. And the way that's done, as we've said already, is with the SGD algorithm, and this is how it goes. So we have a weight, so we have a weight previous, so we have the previous weight, or in the case where we are the first step, we have the initialized or randomly initialized weights minus a learning rate. So we have a learning rate, the rate at which we're learning this data which we've been given, times the derivative. Now in case you have no background in calculus, you shouldn't have any worries, as TensorFlow will take care of this. So here we have learning rate times this derivative of the loss function with respect to that weight. So yeah, we have the weight previous. So that said, if initially we have 0, and then here we have c, let's say c, as we said already, is 2. Now what happens is, for each and every weight, we're gonna take this. So if we want to get the new values for the weight, or for m, so we have m is gonna be equals, its initial value is 0, so the previous value is 0, minus, now let's pick a learning rate. Generally learning rates are picked in the order of 0.001, 0.1, 0.01, 0.0001, and you could continue to 1 times 10 to the, say, -6. So here we're supposing we've picked 0.1, and now we have 0.1. So that's our learning rate times the derivative of the loss. Now what's the loss? Recall we have already seen 3 loss functions in our error management section. So here we're having 0.1 times the rate at which the loss changes with respect to that particular weight. So we have 0.1 times this with respect to m, and the same is done for c. So we're gonna do 2 minus our same learning rate times dl on dc. We've now updated m and c, and then now if we compute the error, we would have y actual minus these new values of m and c are going to be used here. So we're going to have our new m times x plus our new c, and we compute a new error. So we'll have a new error. And so from here, we expect that as we keep on training, we want our loss to keep dropping up to, say, a value of 0, since we want to have 0 loss. Though in this case, we see clearly that it's not possible for us to use just a straight line and obtain a loss of 0, since we cannot pass through each and every point with a straight line. So if we're able to build this kind of model, then we would have a loss of 0, since for each and every point, the actual output is the same as our predicted output. And so we'll obviously have a 0 loss. But with a straight line, that's not possible. So as a recap, we see that we have our inputs and we have our outputs. We have m and c. That's our model parameters. We pass our inputs using our initialized m and c. We get the outputs. We compute a loss. That's we compute the difference between what we actually supposed to get and what our model predicts. We get this difference. We could use a square or just absolute value function. We get this loss, and based on this loss, we modify these values, and then we repeat the same process till our training converges. Our training converges simply means we've attained a point where our loss doesn't increase anymore. So if we have training like this, we could get to this point. You see, at a certain point, we keep on training. That is, we keep on repeating the gradient descent step, which we've seen already, where we update by doing w equal w minus a learning rate times dl over dw. So we repeat the step, which we've seen already, and if our loss doesn't change much or doesn't even change at all, then our model has converged and we could stop training at that point. As usual, TensorFlow does all the hard work for us. And so here we have model.fit. We pass in our x, that's our inputs, x, y. We specify the number of epochs. Let's say 100 variables equals 1. Now we understand what this x and y means. So basically our data set. Now the epochs, or the number of epochs here, is to specify the number of times we are going to update our weights. So the number of times we are going to go through the gradient descent step. And for variables, it has to do with the outputs from our training step. So here we've compiled. Let's correct this. We have, okay, so we have that. We compile, that's fine, and we run this. You see, because our variables equal 1, we are able to get this kinds of outputs. So here we're going to see in real time the values of our loss. Let's stop this. So we stop that, and then we send variables to 0. You will notice that as the training goes on, we don't get to see those loss values anymore. So let's take this back, stop this. You see, variables equal 1. Now we're able to see the loss. So as we go from one epoch to another, we're able to get the mean absolute errors. That's the total mean absolute error, which is an absolute value of our model predictions, or the absolute value of the difference between our model predictions and the actual current prices. When we get into this tf.keras model documentation and we go to compile, you see we could have this right here. We have the definition of compile. We see how by default our optimizer is RMS prop. Now note that this optimizer, or these different optimizers, are essentially variants of the stochastic gradient descent algorithm. So here we get into optimizer. As you could see, we have add a delta, add a grad, add m, and here you see you have SGD. So this is the SGD we've seen already right here. So we can have this SGD. We specify the learning rate. At this point, we understand what learning rate means. We have the momentum. We could increase this parameter so that we could speed up training, and we could also specify whether we're having a Nesterov type momentum right here. So when we say Nesterov true, then we're having a Nesterov type momentum. So that's it. Of all these optimizers, the most commonly used is the Adam optimizer. So you'll see that many scientists and practitioners generally use this optimizer. By default, the learning rate is 0.001, beta 1 0.9, beta 2 0.999, epsilon or 1 times 10 to the negative 7, and the AMS graph type is set to false. To better understand the learning rate, let's take this example. So here we have loss versus weight, like the M or the C, and now we have the derivative of the loss with respect to the weight. So let's consider that this derivative is positive. So let's pick a point like this. We have the weight here is this particular weight, let's say WI. We picked out this point, and we have this derivative of the loss with respect to the weight, or the partial derivative actually. And then we have let's say we have the slope. So the slope is positive. To update this weight from WI to a new weight, we apply this formula. So we have WI minus the learning rate times this positive slope. Now, if this learning rate is too small, let's say 10 to the power of negative 10, so we have a very small learning rate, it's clear that we are not going to have a great difference between the W we obtain after this update, since this is going to be multiplied by this positive value, and W minus a very small number will give us a value very close to W. So there's not going to be a very great change after this update. We're going to have a very small change, actually smaller than this. Now, if R does a learning rate is too large, let's say we take a learning rate of 10 to the power of 3, in that case we have W minus 1,000 times this positive value, then the change is going to be too brutal, and instead of say going slowly towards this point, we are going to actually skip that point and get to this other point right here. And if we keep doing this, we'll actually go away from this point. So we're picking out points which are far away from this point. Now, why is this point important? This point is important because at this point, as we could see here, the loss is minimal. So recall that as the aim of this error sanctioning section, where we're trying to minimize the loss. That said, many times by default or from many experiments, starting out with 0.001 is going to be a good idea, but note that you could always change this. So you could feel free to change this. You could take something bigger. Recall that if you take a bigger value, your training is going to be faster, but risks diverging, that is, risks not leading you towards that minimal loss. Whereas if you take it too small, then you would converge, but your training is going to take too much time. So this value is kind of a great one that is very commonly used. Now, particularly for this Adam optimizer, we have these parameters beta 1 and beta 2. Now here, beta 1 max and beta 2 max are all 1. So taking a value like 0.9 and 0.99 here means we're taking high values of beta 1 and beta 2. If you want to speed up training, you will want to increase the values for beta 1 and beta 2. By default, this values are set to 0.9, 0.99. Now, when doing or carrying out computations with respect to the Adam optimizer, we're trying to avoid dividing by zeros. So we have this epsilon parameter here, which is by default 1 times 10 to the negative 7. Now, if we want the AMS grad variance of the Adam optimizer, you could set this to true. So that's it. We now have from TensorFlow.keras.optimizers, we're gonna import Adam. So we've imported that. That's fine. now we're gonna make use of that. So actually in this compile we have optimizer equals Adam, and that's it. So we have defined our optimizer and we define the loss. So let's run this again. We actually had an error, so let's take this Adam, run that. That's fine, and there we go. Now we've been getting these values for loss. What if we store this in a variable? So we could have history equal model.fit. So this time around, after doing the training, we'll be able to recall all this loss values we got during training. There we go. We have history.history. We run that, and here we got all our loss values. Let's climb up, and you see here we have this dictionary, we have loss, and then we have this list of all the loss values. We now import matplotlib, so we now paste this out here. We specify this plot. We have history.history, which we've seen already, and we specify the loss because this is actually a dictionary. We pick the loss. We specify the title, y label, x label, the legend, and then we show this plot. So this is what we get right here. We see how we drop our loss value is dropping, but the rate at which is dropping is actually quite small. So what if we speed up the training by modifying the learning rate? So right here we have learning rate equal 0.1, or let's just pick a learning rate of 1 and run that. We run this and we see that the loss actually drops faster this time around. From here we move on to performance measurement. We're actually measuring how well this model performs, and one common function used in regression problems like this is the root mean square error. You should note that it's not in every case where you would have the performance measurement function similar to that of the loss, as these two are actually quite different concepts. For the performance measurement, or making use of the performance measurement, we are able to see whether these two models, so supposing we have two models, model 1 and model 2, have the same performance or do have different performance, and which of them outperforms the other. So if we run performance measurement, we'll be able to say whether model 1 outperforms model 2 or model 1 underperforms model 2. That said, we could include this metric in here. So we have the optimizer, loss, and the metric. So we have this root mean square error metric, which has been added and which has already been imported. So we've imported this here. Note that this is a metric, not a loss. So we have this metrics, we've imported root mean square error. And if that's fine, we could go ahead, compile, and start our training again. Now you will notice that both the loss and the root mean squared errors are being printed out. So this is what we could see now. After the training it will be done, we'll be able to plot these two out. So here we have the loss. You can see we run the loss and we have the root mean squared error. So this is what we had put in. To get this exact string right here, you could do history.history. So here we have the history, and you would see that, okay, here you have the loss. So we have the first key loss, then we have this list of all losses, and then we have the next root mean squared error, and then we have this list made of all the root mean squared error values. So that's how we get that. We've plotted it out, and this is what we have. Another method which comes with TensorFlow models is the evaluate method. So here we could have model.evaluate, and we simply pass an x and y. So we evaluate our model this way. So you see, we've evaluated our model, and we have the model's loss and the root mean squared error. From here we move to validation and testing. To better understand validation and testing, let's take this simple example. Imagine you get into class, that is, you get a class on the first day. and you have been taught some course materials. So you've been taught these course materials throughout the whole term, or say the whole semester. And then at the end of the semester, the teacher who is feeling lazy tells each and every student to feel free to produce their own exam. And after producing this exam, they should sit for this exam produced by themselves, so they could feel free to come up with any kind of question, sit for this exam, and after sitting for this exam, they mark their scripts by themselves. It's clear that most students will have marks greater than say 18 and 20, and this is simply because this exam has been set by the students themselves. Now, it may happen that a student has followed through the coursework and mastered everything, and then set real questions or tough questions and got this mark of 18. Same as other students may not have thoroughly gone through this coursework and produce very easy questions, which will get them a mark of greater than 18 without any much effort or without mastering the coursework. And so that's why this strategy is very dangerous, as we need that external validation from our teacher. And so far, what we've been doing here is kind of like the first method, where each and every student produces the exams, sits for the exams, and then marks the exams by themselves. And that's simply because here we're using our full data set, training on this full data set, and evaluating its performance without taking into consideration data that the model has never seen. So the idea is to be able to create a model that when it sees new data is able to come up with a reasonable current price, which is as close as possible to the actual current price. And so when dealing with machine learning models, it's important to say break our data set into two parts. So if you have like in the example we're working on 1000 examples, you could break this up such that you have 800 examples which you train your model on, and then you could test that model on another 200 examples. So here we've never, or the model has never seen this part of your data set right here. And this is one very important use of the shuffling, because with the shuffling we are sure that there is no bias in the way the data set is constituted. As now, if we just break this up, we have one part for testing, another part for training, which has been randomly built. And so as we're saying, if a model, for example, has a performance of say root mean square value equals, let's take say 5 on the training data, so on this training data, and then on the test data it has a root mean square value of 50,000, then it's clear that this is a very poor performing model, as it does well only on data it has seen, but on data it hasn't yet seen, it doesn't perform well. And so recall, machine learning is all about empowering the machine to do stuff humans are known to do. And obviously humans use some intelligence in doing all these tasks. So if you want to build a model, you have to ensure that it performs well on data it has never seen. And so we always have to split our data set. So firstly, we shuffle our data set, very important. We split this data set before proceeding with modeling and training. Now, sometimes we don't want to wait until our model has trained before testing it out and discovering that it performs very poorly on data that's never seen. So what we want to do is, while doing the training, we want to be able to see how it performs on data it has not seen. And that's why we have a validation set. So that's why you need a validation set. We've seen that we need a testing set, as you can see here, and then now we need a validation set. And that set, here we could reduce our training 600, and then we increase this, so we have 200. So we have our data set of 1,000 data points, which is broken up now into our training, validation, and testing. Now note that if you have a data set of, say, let's increase this, of this, how many? This is 100. If you have 100 million data points, then taking, for example, like previously we chose this. This is actually 60%, 20%, 20%. But if we have 100 million data points, we could always use 90% here. Here we could use 5%, and here we could use 5%. Reason being that since the total data set is very large, getting 5% of a very large number is already quite a huge number of samples. So that is good enough for us to build our validation and testing sets. We get back to our data set preparation. Let's include a cell. Here we specify our training and validation, or training, validation, and test ratios. So we're gonna use 80% of our total data for training, or 10% for validation, and 10% for testing. The data set size, we have it here. The length of x is 1,000, and we run this. We added another code cell, actually right here at this. Then we have this x train, y train, made of elements in the top 80% position. As here we have data set size. So if you have 1,000 times this ratio, will give us 800, and we have the first 800 elements. Same with this. We print out the x train shape, and we could do same for y train. So that's it. We have this shape right here. So that's it. We have broken this up. 1,000, now we have 100. Let's do same. So let's add this and do same now for the validation. So instead of train, we have val, and down here we have val. So we have val, and now we want the next 10%. So what we're gonna do here is we simply copy this. That's it. Here we have the validation ratio, or rather we're going from the train ratio actually. So we have the train ratio up to the train ratio plus the validation ratio, because we're going from 0.8 now to 0.9. That said, we would have this plus the validation ratio. So that's fine. Next, let's just copy this. So we've copied this. There we go. Take this off. We get the next values. So that's it. We've gotten this next values. We have x right here. We have x val, and here x val. So we run that. Let's close this right here. So we have this. We run it. That's fine. Okay, so now we have the next 100, and at that we now get the last 100. So since we have no other section, all we need to do is just specify this still validation actually, but right up to the end. So we have that. We run it, and there we go. We have the data set which has been split into the training, validation, and testing. We have x train, y train, x val, y val. Yeah, we have x test. This should be x test. So let's change this. X test, x test, x test. Okay, so we run that, and that's fine. Now, one important point to notice: you have to avoid information leaking from the training into the validation and the testing. So this means even when doing normalization and you're trying to adapt your normalizer to your data, you have to not use the validation and testing. You just have to use the training. So here we're going to use only the training set to adapt our normalizer to our data. From here we have to modify the way we do our training. So here we just have to specify that we have X train, we have Y train, and then our validation data is equal. We have this X val and Y val. So that's it. So here we specify X val, Y val as your validation data, and then you have X train, Y train as your training data. Now note that when doing this, so with a validation data, you actually specify X val, Y val, but there is another argument which is the validation split, where you just specify the fraction of the training data to be used as validation data. So again, here as usual, you could go through the documentation. You see you have shuffling, which you could do, but which we've done already. You have all these other arguments which you could check out in this documentation. Getting back to the code, we run this, we run our training. Now training is done. You could notice how we have this extra outputs here, the validation root mean squared error and the validation loss. So you could see, you notice this right here. Let's get straight away into putting these plots. Again, let's do history. Let's add this cell here, history.history. And here we see we have the validation loss. Go up, we have the root mean square error. We should get the validation root mean square error. So let's scroll down. There we go. We have the validation root mean square error just right here. So now we have the training and validation, which has been outputted during training process. Recall the use of the validation is for us to be able to see during training how well our model performs on data it is never ever seen before. So let's go ahead and do some plotting. Here we have our loss. We have this right here. We specify the validation loss. There we go. Let's run that. Okay, so we see our validation and training loss. Let's put this here. We have val loss. So we specify the legend. Okay, there we go. We have our training data and we have our validation data. We see that our validation data, our model does better on our validation data actually, as we have lower loss values for the validation data. We could repeat the same process with the root mean square error. So here we have that. There we go. We now put in your validation. So here we have validation, and then we have validation. We run that, and it's kind of like similar. Here the validation does better, or the model does better on our validation set. From this point, let's take this off. We get back to model evaluate. So let's evaluate our model. By just specifying this wouldn't help. So you could actually put this X val, Y val. So no, we're not evaluating anymore on our training data, but now on the validation data. And we could also now evaluate on our test data. Recall validation was used during training. We saw how it performed during training. Now we're gonna evaluate our model on data it has never seen. So we evaluate on our test data, and this is what we get. We see we have this loss and this root mean square error value. At this point, we've trained our data, or we've trained our model on our data, and we can get to that long awaited part, that is testing our model. So here we are not just evaluating our model or doing some validation, but we are passing in data, and then we're allowing our model to predict the car price for us. So that said, let's get straight away into that. We have X test, which we know already, or which we built already. That is it. X test shape. There we go. Let's pick out a value from this X test. Let's just say X test 0. So what we do is model.predict. So now we've trained our model. We now do model.predict, and we pass in X test. So here we don't need to pass Y test. We just pass X test. So here we pass X test, and our model should predict the car price for us. Now passing in X test, we have all these predictions. So because we have 100, you see shape, there we go, we have 100 different elements. So for each and every data point, for each and every input in our testing set, we have all these outputs. Let's just pick out a few. Let's say we want just the first. So that's it. There is this warning, which is normal because the input shape here has to be of type batch size by 8, but here we're sending this of shape 8. So we should do expand dims. In case you don't understand this well, let me repeat again, or let me just do this. Test 0 dot shape, that's a shape, you see, that's test 0 shape. Now x test dot shape, that's a shape. Now this model, as we defined previously in our input right here, in our input, takes in a batch size by 8. So here we have to ensure that if we're passing in any data, it has to be of the shape. So now we have put in this, and what we know to do is to expand dim such that we leave from the shape 8 to the shape 1,8, so that it takes this form. And when it's like this, it means our batch size is 1. So that said, let's do expand dims. We've seen this in the previous section. We have expand dims. There we go. We add this axis equals 0. That's fine. And we run that. So that's it. Everything works fine now. Let's take this off. We will run that again, and we have our response. So this tells us that for our first point in our data set, or first input, our car price prediction is this. Now, this is very interesting to view, but what if we compare this with what the model, or with what the data already presented to us? Because it's true we label this as test, but we know the actual values, so we know the actual car price. And what if we compare it with this predicted car price? So that said, let's look at y test 0 and check out this value. So here we have $130,000, and here we're predicting $11,940. So clearly our model is performing very poorly. To visually understand this poor model performance, we are gonna plot a bar chart showing the predicted and true values shown side by side. Let's take this to say 20, and there we go. As you could see right here, let's scroll. Okay, that's fine. As you could see, we have this blue, which is for the predicted, and then the orange for the actual values of y. So we have the predicted and the actual prices, which is shown to us. Now, the way we plotted this out is quite simple. We have we have the figure size, we have this bar. So here we're plotting out some bar charts, and we're specifying the position of each element with respect to the bar chart. Now this in here, if we plot this out, so print out, we also use a numpy to get this. So let's run that. And you see that this is a list comprising of values from 0 to 99. So this permits us get the position for each and every element. So we have 100 different positions, and then the width obviously is clear. Let's reduce the width so you understand that. You see that visually. Let's take this. Let's increase it to 1. So we've increased the width. You see this becomes very large. Now let's take that back. Let's say 0.1. You have this, you see, becomes very thin, and that's it. So we could play around with the width. Now once we fix a position, say we've fixed this position, we now move width steps further. So that's what we do. And we have that passed in here. We have the label, x label, y label, and then we plot that out. So that's how we come up with this plot, which shows clearly that our model is performing very poorly. And this takes us to our next section on corrective measures. This poor model performance actually has a name. It's called underfitting. So when your training loss looks like this and your validation loss, normally validation loss should be above the training loss, but in some cases, like as we just saw, it was below the training loss. So we have our validation. So let's say we have our training and then we have our validation losses, which are like this. And even after training for a long period of time or for so many epochs, we are not able to go below a certain threshold. This is known as underfitting. And the idea here is to bring these loss values like this. So we want to modify our model so that we could have better loss values. That's we could reduce our loss values as much as we can. That said, in order to do this, it suffices to make our model more complex. For now, the model we're having is like this. So here we're having this simple regression model where we have our inputs right here, M1, M2, F2, M8, our weights, and then our bias C. We add this up and then we have our output. So what if we take this off and then we add up more neurons right here? So instead of just having one, we're gonna stack up more neurons, but they are doing basically the same thing. So we kind of like repeating the same process here. So we're gonna have this linked to this one linked to this, the same way it's linked to this one we had previously, this linked to this, and so on and so forth. And then we repeat the same process for this link. Then from here, so here we have this dense layer. From here again, we could add more dense layers. So this is what we call a hidden layer. Here we have a hidden layer. We add more. So here we could have one, and you see here all these are all linked up this way, and it's actually the same operation, mx plus c. So basically we're taking this weight times this plus bias, and then we get in this. We take this times its weight, and we get this plus the bias. We have this, and then we continue the same operation. So we have this stacked again. We have this first hidden layer 1, hidden layer 2, and we could even go to another one again. So let's add this 2 here. Let's add this other hidden layer. Let's do this. There we go. We've created this third hidden layer. So here we have our inputs, and we have 3 hidden layers. And obviously, since we just predicting a single price, from here we could have this. So we now have this our output layer here. So input, output, and then hidden layers. Here we have this. So we have this dense layer, and we have also this dense layer. Let's try to write out or sketch out some TensorFlow code here. So basically we're gonna have dense. So we have a dense layer right here, and what does it output? That is, this first dense layer has 3 outputs, basically, comma, and then we move to the next dense layer. So if we're having a list, we have this dense layer right here, 3 outputs, unlike the previous one which had just 1 output. Now we have this dense layer with 3 outputs. We stack the next dense layer. So you see the way it's easy to carry out all these operations with TensorFlow. We stack the next layer with 4, so we have 4 outputs, and then the next we have 2 outputs, and then finally we have 1 output. It's very important to ensure that you have just 1 output, because that is kind of like matching up with our data we have at hand. So here we have 1 output, and we close this list. So you could put this in bracket and then have the sequential and all of that, and then you have this. So that's it. We have seen how we create this very easily with TensorFlow. And there is one point we need to mention, and that's the activation functions. Now, activation functions, simply put, are nonlinear functions which add even more complexity to the model. You saw how previously we had these inputs, and then we had just 1 output, and we were linked linking them up like this. Now we've made this model more complicated. We've added more hidden layers so that we could learn more complex information stored in our data set. Now another thing we could do is add in the activation functions, as I've said already, and make this model even more complex. Common activation functions are the sigmoid activation function, the tanh activation function, the ReLU activation function, rectified linear unit, and the leaky ReLU. So we could have this ReLU, that is when x is greater than 0, we maintain x, that is x remains the same, or the output equal the input. But when x is less than 0, the output becomes 0. Now here, when x is greater than 0, the output is the same. When x is less than 0, the output is negative certain alpha times x. Hence the term leaky, as this alpha is generally a very small number. So if we have 0.1, we could have negative 0.1x, which is kind of like giving us very small outputs, which are kind of close to 0. Now we have the sigmoid activation function, 1 divided by 1 plus e to the negative x. See, looks like this. The tanh e to the x minus e to the negative x divided by e to the x plus e to the negative x. For now, we're going to use this ReLU activation function, and you'll see subsequently that all these activation functions could be gotten from TensorFlow Keras activations. Now, you should also note that if we were to apply, for example, the sigmoid activation function right here, what we'll do is just after summing up, or just after multiplying this weights by the inputs and getting the outputs, once we have this, we are going to do sigmoid of this. So we do sigmoid. So actually for at each and every neuron right here, we have the sigmoid of this. So here we have sigmoid of all computations, or the output of the computations. Here we have sigmoid, here we have sigmoid. And in the case in this layer, we have the sigmoid. Then for each and every neuron, we have sigmoid. If here we have, for example, ReLU, then for each and every neuron, we have the ReLU activation. We now have all that's needed to make our model perform better and stop underfitting. And so we come right up here. We have a dense layer now. Let's say we have 32. So our output will be 32 neurons. And then from this, we have 32 again. And then we stack up another one. And finally, we have this layer right here. Recall that we've added up these other dense layers, but at the output, we need to have just one neuron. So it's important to ensure that our output here is 1. We now specify the activation. So we have activation equal ReLU. And here we do the same. For our output here, we are not going to specify any activation because we don't want to interfere in the way our model comes up with its outputs. That said, we could run this. And to make our model even more complicated, we could increase this value. So we could take this to 128. Let's run that again. You see that we have many more parameters we are training on. Again, we are still having the 17 non-trainable parameters. So when we had this, you see we had 17 and 9 trainable. Now that we have this, you see the number of trainable parameters increases while the non-trainable parameters remain on the same spot. We have the 17 non-trainable parameters, which is logical since our normalizer remains the same. Now that said, we've done that. We could plot our model. So we see this plot right here. That's a clear plot. We see how we live from the input to this dense layer. You see here known by 8, known by 128. This next dense layer, this other dense layer, and finally this dense layer. From there we compile our model. Let's take this. So here we have 0.1. Let's run this. And we're ready to fit our model. So let's run that. We now notice how this loss right here It's a smaller order of magnitude as compared to what we had previously. Notice how this drops from 100,000, about 144,000, and goes down to like 30,000. So that's it for this training. We now go ahead and view our plots. So there we go. We see we have totally different plot. Now we live from this, and then we actually drop to about 30,000. Also notice how this time around we have a validation loss, which is higher than that of the training. And this is normal because obviously the model was trained on the training data, so it would tend to perform better than data it wasn't trained on. Now, if a model performs very well on the training data and doesn't perform well on the validation, then we have a problem, which is known as overfitting. And we're gonna treat this in subsequent sections. So for now, we just continue. We plot out the root mean squared error. Notice, recall how we used to have values of this order, 334,000, but now we are on 30,000. Okay, let's run this. What do we have? Okay, so we have something very similar to the mean average error. That's our loss. That's fine. We evaluate our model. So that's it. We have this loss for our model on our test data. So here's our loss on the test data. Here's our root mean square error. From there, that's fine. Okay, we do this widespread, and here's what we now obtain. We notice how this model performs way better than that previous smaller model. And as you could see here for this particular test data point, you see how what our model predicts is exactly the actual current price. Our model isn't perfect, but is doing quite well. At this point, we've taken up some corrective measures and our model now performs better. What if we look at how to load our model even faster and more efficiently? This can be done thanks to the TensorFlow data API. So right here you have tf.data. You could go to the overview, and then for now we check on this data set right here. This class is made of many methods, so you have these different methods here. For now we'll start with the from tensor slices method. So from here we're going to adapt our code to use TensorFlow's data API in order for us to gain from all the advantages that come with it. Now note that when you're working with a data set of say 1,000 elements, you wouldn't see, or you wouldn't clearly notice the advantage of using this data API. But as your data set gets larger, it becomes very important to master how to use this API. Now that said, we are going to redefine our X-train. So yeah, we're going to say train data set, and we're going to have tf.data.dataset.from tensor slices. So that's it. Now we're going to have this tuple which we create, and then we pass in X-train and Y-train. So that's it. Now we've gotten this. The next thing we're going to do is we're going to shuffle our data set. Now we've already done shuffling, but in the case where shuffling wasn't done previously, you could do the shuffling very easily now. So here we have this dot shuffle, and we specify a buffer size. Our buffer size, let's say 8, and let's see exactly what this buffer size actually means. So here we have a seed, and you have reshuffle after each iteration. Now let's look at how this buffer size, what it means exactly. So here we have been told if your data set contains 10,000 elements but buffer size is set to 1,000, then shuffle will initially select a random element from only this first 1,000 elements. So it's just like saying I'm picking this first 1,000 elements, and I want to carry out my shuffling only from this first 1,000 elements, such that when I'm picking a random value, obviously when we're doing shuffling, we're picking out random values in a random order. So when I'm picking up my random value, I'm going to pick it up from this first 1000 values. Then as I said here, this once this element is selected, its space in this buffer is replaced by the next 1000 first element. So if we have a data set like this with 1, 2, 3, 4, 5, 6 elements, and then we want to shuffle with a buffer size of 3, in this case we'll initially select or pick up a random value from this here, from this buffer, from this first 3 elements. And then if suppose we pick this random value right here, what we'll do, let's take this, let's annotate this 1, 2, 3, 4, 5, and 6. So if we've picked up 2, we've picked up 2. Now we're gonna have our next buffer to be like this. We're gonna now have 1, 3, and 4. So this next element is gonna be added to our buffer, and then we'll have this 5, 6, 5, 6 right here. And once we're done with this, so once we pick up another random number, let's say we pick up 4, we pick up 4 here, our next buffer will be 1, 3, 5. So we have 1, 3, the next 5, 1, 3, 5, and we repeat this, and so on and so forth. So that's how we work with this. That said, yeah, we could also pick reshuffle each iteration. So after each epoch, we're gonna reshuffle again. So that's it. We've had our train data set shuffled, and then we have again train data set batched. So we could just add this right here. Actually, we could say we've shuffled, then we batch this, batch size 32, and then from here we could do prefetching. So let's do some prefetching. Prefetch. We're checking the documentation to see what it takes as argument. To see again here we have a buffer size. Now we are told that this allows later elements to be prepared while the current element is being pre-processed or being processed. And so if we have a data set like this, so let's suppose that we have these 3 elements, element 1, element 2, and element 3. So currently we are actually training on this data, or on this batch here. We're actually training on this, and generally when we train on this, as we have to train, after training we have to load this data, process it in case we need to process it, and then so let's suppose that this is processing time. So for our key, this is training time. After we process, then after we train, after we process this here, so after we process that, and then we train. Initially we even process this, so initially we will have this. So we process this one, we train, we process, we train, we process, we train. Now what if instead of going through these steps, we load? So here we start by loading, we load, and then while we're training, we actually loading up our data. So we could be loading up our data while we're training, so this could be done. And then after training, we have this loaded up data already, so we just continue with the training. And then from here, again while we're training here, we loading up, so we're loading up. Suppose we load this up like this, and then from here, from this point, we train. So recall we have 1, 2, 3 train steps or train blocks. So at this point we add our last block, so that's it. So from here we see that we take less time to load and train our data as compared to this first method. So working with prefetching is very important. Now this prefetching takes up a buffer size which can be auto-tuned. So here you have tf.data.auto-tune. In case you don't want to specify the buffer size, you could just simply allow TensorFlow dynamically tune this buffer size for you. Now that said, here we have this. So we have prefetch and then tf.data.auto-tune. That's fine. So that's our data. Let's take this off. So we now have train data. our train data set. Let's add this and let's run this actually, and then for t in train data set, we print out t. Now we've okay, we've bashed that, so let's print out t, and then let's print out just the first element actually. Let's say for x, y, so we could print out x and y separately. So we have x, y, we'll print out just the first. That's it. You see, we're gonna have this like this. Let's go up. Okay, so yeah, we see we have this right here. What's its shape? So we have 32 by 8, which is normal, batch size by 8, and then we scroll down. Yeah, we have 32 by 1, which is normal. So that's very normal. We've batched our data and we're ready to train this data. So let's just recopy this and do same for the validation. Right here we have validation, val data set, and we have val data set. Don't forget to change this, so you have val. That's it. That's fine. We run this, our val data set, and now we go to the test. So right here you could also do same for the test. We have that test. There we go. Test. So that's what we need to do to convert this so that we could use it as data, or we could work with the TensorFlow data API. We don't do any modifications on the model. All we need to do here is come and specify train data set, and then for validation we have our val data set. So here we have val data set, so that's fine. You see training has started and everything seems okay. So we'll now go ahead and view this right here. So that's what we get. See, it still continues dropping. Actually, we could from the previous training we would have continued training, so we could have increased the number of epochs. That's fine. Let's look at this as well, and we could evaluate our model. Now note that this actually isn't very different from what we had previously, as you may feel like this is producing a different kind of plot, but the model is in its current state already had a loss, or was had a loss of about 30,000. So if we have to recompile our model, so right here, if we have to run this, recompile our model and fit, you get to see that it isn't much different from what we had previously. So this doesn't actually come to better our model performance. Actually, it comes to speed up the training, so you wouldn't expect to have better loss values with a tf.data, but instead you could attain this better performance faster. So let's run this again and you get to see that it's kind of like similar to what we had already, so that's fine. We run this as well. You could always increase the number of epochs. You'll see that here, that's what we'll get. And see, we could predict with this, fine. And now we could go ahead and view this on our bar chart. So we look at this, similar to what we had already, so that's fine. We now master the basics of working with the data API, though in subsequent sections we'll look at even more interesting ways of working with this API. That's it. Hope you enjoyed this. Thank you for following up to this point. Don't forget to like, subscribe, and share. See you next time.